Hello again. This is going to be the second example problem that we look at for general motion, and I have a couple of problems with this one, but I think it's going to be interesting to work through anyway. The circular concrete culvert rolls with an angular velocity of omega equals 0.5 radians per second. When the man is at the position shown. At this instant, the center of gravity of the culvert and man is located at point G. You can see on the picture here that G is located 0.5 feet away from the actual center of the culvert. The radius of gyration about G is kg equals 3.5 feet. So I'm going to want to keep that in mind. I need this to calculate moment of inertia. I have not in any of my videos so far talked about radius of gyration, but the moment of inertia about a point is equal to the mass of the object times its radius of gyration about that point squared. So they give us the mass, they give us the radius of gyration, we can find the moment of inertia. All right, the combined weight of the culvert and man is 500 pounds. Assume the culvert rolls without slipping and the man does not move within the culvert. Okay, so in this situation, we have moments created due to the rolling of the object. There's friction, which causes the rotational motion, and all of this is created by the man being off at some location on the side. There's going to be some weight force, some sort of weight force, which is created by the man that causes rotation, as well as the friction force, which also causes the rotation. So I'm a little bit concerned and curious about two different free body diagrams here. One very important part of this is it says assume that the culvert rolls without slipping, that's one, and the man does not move within the culvert. That's really important. It means that the man is stationary while the culvert rolls. There are a couple of different ways to solve this problem. One where the man is truly stationary, one where he stays in the same relative position, so he's moving to the right, but not like kind of rolling with it, if that makes sense. All these different ways of solving this problem yield a different result. And for that reason, I wouldn't like this problem in mastering engineering. I think there's several different ways to solve it based on different assumptions that are all pretty okay. And who knows what mastering engineering would look for. But fortunately, I don't intend to post my solution to mastering engineering, so I can just do it my own way. My way will be valid, but under maybe a different set of assumptions than they would have wanted me to make on mastering engineering. So what I'm going to do is I'm going to draw a free body diagram of both the combined system. That situation simply has a weight force here. The weight force there is 500 pounds. There is also a normal force, and there is a friction force. The friction force I have pointed to the right. I'm going to change that. It's definitely going to be pointing to, wait. I was going to say it's definitely pointing to the left, but I'm not so sure anymore. It's going to rotate clockwise as for sure. Oh goodness. The clockwise rotation is created by a moment about G. You know what? I'm just going to draw it in a particular direction. You'd think this would be easy, right? So you'd think that because it's definitely going to accelerate rotating in the clockwise direction, therefore there's a friction force that points to the left, creating that rotation. But you'd also think that because the man is exerting his, he has his weight to the right side of the culvert, that it's going to be accelerating motion to the right, which means that you might think the friction force points to the right as a result. Those two different options are both worth considering, and I'm going to hopefully solve this problem in a way that sorts this out. So I have a friction force here and a normal force there, and we will work out the details as we work through the problem. There's one thing I know for sure, and this is a motion issue, not a force issue. The acceleration of the ground, here's that problem again, the acceleration of the ground down here, there is no tangential acceleration. there's no acceleration left to right of the ground, and if it rolls without slipping, then the acceleration of the bottom of the wheel is also 0. At least it doesn't point left or right at all. That's important. Because there is an omega, it does have a normal acceleration pointed upward. So I'm really struggling to do this. Okay, it does have an acceleration upward. So I know the acceleration of the bottom of the wheel, if it's rolling without slipping, it points up. It's equal to 4 feet times omega squared. Omega is 0.5. That squared is a quarter. So what we have here is the acceleration of the bottom of the wheel points straight up at 1 meter? No, foot. The acceleration of the bottom, which I'll just call B, is equal to 1 foot per second squared J hat. It points straight up. The motion of the center is going to can be thought of in relation to that, and the acceleration of the center of gravity can also be thought of in relation to that. As this thing rolls, there's one thing I know for certain. Let's take note of what we know. I know that the acceleration of O points to the right. Basically, I know that O travels in a straight line path. I know O travels in a straight line path because I know that this is a circle and it's going to be rolling, and O doesn't get any farther away or closer to the ground, so it's point straight to the right. I also know that AG is equal to AO plus AG with respect to O. This term points to the right. This term has an alpha cross R and an omega cross R term relative to O. So the omega cross R term points to the left. That is 0.5 feet times omega, which is 0.5 radians per second squared, and that's in the negative I hat direction. And it also has an alpha term. I'll say that alpha is going to be clockwise also. So it also has a downward negative 0.5 feet alpha J hat. Again, I am still just talking about motion, nothing else. So this is a little bit, I'll say interesting. From a motion perspective, again, I'm still not talking about my free body diagram. I also know that the acceleration of O relative to the acceleration of the bottom follows the same sort of result. AO with respect to B and all that. I know this points to the right. I know this points up at 1 meter per second. I keep saying meters. 1 feet per second squared J hat. And this is due to circular motion of A about B. It has two terms. The relative position is vertical, so the two terms are going to be an R omega squared term that points down. The R is 4 feet. Omega is 0.5 radians per second squared, and it points in the negative J hat direction. And there is an R alpha term. The R here is also 4 feet. I have alpha being clockwise, so my R alpha term of O relative to the bottom points to the right. That's 4 feet times the unknown alpha, and that's in the I hat direction. So if I'm thinking about this, let's consider I've got AO, which moves to the right, so I'll just label it like this. AO I hat equals 1 feet per second squared J hat plus 4 feet alpha I hat minus 4 feet times 0.5. This has got to be squared, so that's my mistake. J hat. And let's just see if this ends up working out. I know that these two things have to cancel, and they most certainly do. This is R omega squared, so that omega's got to be squared. 1 negative 4 times a quarter, These two cancel out, and that leads me to conclude the following. The acceleration of O is equal to 4 feet times alpha. And it's accelerating to the right? So that's what I know about O. This is actually just like a universal result for the center of a wheel. The center of a wheel is always accelerating at r alpha where this is the radius of the wheel. And if it's accelerating to the right, it's r alpha to the right. If it's accelerating to the left, it's r alpha to the left. And that's that, okay? Does that actually say radius? What good? You can tell that my board work and my board handwriting is a lot better than my tablet handwriting. So, okay, cool. I want to know this because I want to know the acceleration of g with respect to O. So let's talk about the acceleration of g. I'm now going to take this equation and bring it down. I have the acceleration of g is equal to AO, which we just found. I'm going to just write 4 alpha I hat plus, and then I got these two terms here. They're both negative, so I'm going to maybe be ready for some minus signs. Minus, for the I hat term, sorry, I need to be up here. 0.5 times 0.5 squared, so 0.5 times 0.5 squared, that's going to be what? 0.125? 0.125 I hat. And then also minus 0.5 alpha j hat. This is important. Let's group the like terms. 4 alpha minus 0.125, that's the x component. And then for the y component, we have 0.5 alpha j hat. This is AG. We will need to keep that in mind. Without this, we cannot solve the problem. We'd have to do something like this regardless of how we approach this, and there are other ways to approach the problem, but we need to know something about the motion, and this is all about rolling without slipping. So far, I have only considered the fact that this is rolling without slipping. So let me go ahead, make a new page here, move over to that. Let's put the image of the problem back at the top of the screen, and let's bring that equation over. AG equals 4 alpha minus 0.125 I hat plus, just do you remember what it said? Yeah. Minus, okay, minus 0.5 alpha j hat. Cool. Now it's time to start thinking about our free body diagram. Our free body diagram I'm going to put back on the picture. I've got a normal force, I've got a weight force, and I've got a friction force. Maybe that friction force is pointed the wrong direction. We will soon find out. So, sum of the forces in the x direction equals F, and that's equal to M times AGX, which is this. 4 alpha minus 0.125 I hat. And then I've got sum of the forces in the y direction equals W minus, well, let me reverse that, N minus W, and that's equal to M times AGY, which is negative 0.5 alpha. And now I'm going to sum the moments. I think the most convenient spot to sum the moments about is going to be the center of gravity, G, because we know the moment of inertia about G. So if I sum the moments about G, I'm actually going to leave myself more space. So let's move down here. If I sum the moments about G, first of all, let's actually think about the forces. What forces create a moment about G? Well, F does. 4 feet is the vertical distance. It's creating clockwise rotation. So that's positive. 4 feet times F, it's a little bit misleading. I'm going to put parentheses around that. F being the friction force. 4 feet times F, then plus, oh, actually that's minus, the normal force, which creates a moment about G, minus 0.5 feet times N. The weight force does not create a moment about g, and this is equal to Ig alpha. Ig is equal to the mass times the radius of gyration, which is given, squared, times alpha. The way I drew alpha on my picture and I wrote on my equations, it's clockwise, so I really need to label it as being negative here. So I'm going to throw my negative sign into this equation as well. My alpha is negative. All right, so big question. How many equations? How many unknowns? Well, as far as equations and unknowns is concerned, this is an algebra problem where I have 1, 2, 3 equations. Because I put the acceleration of the center of gravity in terms of exclusively alpha, I have 1, 2, and 3 unknowns. And that's great. Oh, I need to underline the alpha here. The system of equations is not super great. It's not super convenient. I've got f and alpha in this equation, n and alpha in the second equation, and I've got all 3 in the third equation. And perhaps there's a way we could work this out a little bit better. I think that there likely is. We could have summed the moments about this point here, which would have eliminated 2 of our unknowns. The equation would have been a little bit rougher to build, but would be simpler algebraically. So I'm going to go ahead and do that. I'm going to go ahead and cross out this equation, and we're going to instead sum the moments about B. Sum of the moments about B has only one force creating the moment, and that is just negative 0.5 feet times W. W was given, you might recall, as 500 pounds. So I'm going to go ahead and plug that in now. 0.5 feet times 500 pounds. It's negative not because it points down, but because it creates clockwise rotation about point B. Remember, B is the point at the bottom of the culvert. This is equal to M, well, I'm not going to write it like that, R G cross O, that is, where is G with respect to O, crossed with MAG, plus IG alpha. And you're probably seeing it, this equation is only going to have alpha, because I know AG in terms of alpha. I worked that out in the first part of the problem, and this is also just alpha as well. So let's work it out. Like I said, think of this as a force. I have, let me draw a little picture here. This point. I have this point where the center of gravity is. I have AG, which is equal to this, to the right and down. So I'm going to go ahead and label that. To the right, we have 4 alpha minus 0.125, and down we have 0.5 alpha, I do believe. Yeah. And we're finding the moment that quote-unquote force creates about this point here. Well, the horizontal force creates a moment due to the vertical distance, and the vertical distance is 4 feet. So let's write this out. 0.5 feet times 500 pounds equals this one first, 4 feet times M, I'm going to leave M as an M, times AG, which is 4 alpha minus 0.125. That is a clockwise rotation, so this is going to be negative overall. Then the vertical force creates a moment due to the horizontal distance. That is also clockwise. Negative 0.5 feet is the distance, and then MAG, M times 0.5 alpha. This is R cross MAG. It's the moment of force created by the acceleration. And I just took the acceleration, broke it into its x and y components, treated it like it was a force, and found the moment. Remember, you're finding the moment of MAG, not just AG. So that's why I multiplied by the mass here. And, there it is. I thought I forgot for a moment. So Oh, and I'm not quite finished. I also have AG alpha. This is going to be minus IG, which is m kg squared times alpha. Why minus? Minus because I drew alpha clockwise, and all of these equations are based on alpha being clockwise. For this problem, this is the positive direction, so this is a negative term because my alpha is clockwise. This equation is one equation, one unknown, and it can totally be solved. I'm going to go ahead and throw this into my calculator and find alpha. So here we go. Negative 0.5 times 500 equals negative 4 times, what's m? Let's point out m is equal to 500 pounds divided by 32.2 feet per second squared, which this is going to be in slugs, some number of slugs. I'll go ahead and do that. No, I'm not going to. I'm just going to leave it. This will go into my equations as written. 500 divided by 32.2 times 4 alpha minus 0.125 minus 0.5 times 500 divided by 32.2 times 0.5 alpha minus 500 divided by 32.2 times 3.5 feet, which is kg, squared, times alpha, and I'll be solving for alpha. I'm going to check my equation before I get too far along in this. I think it's good. I don't see anything immediately wrong with it. Just once more. 0.5 m squared. Yeah, this looks good. Okay, so my alpha is 0.582, we'll leave it there, radians per second, which is actually pretty fast. It's only got me slightly worried that this, radians per second squared, my mistake. Only has me slightly worried that this culvert is accelerating so quickly. Ooh. Any issues worth worrying about? Well, you know what? I'm curious. I hope that the Mastering Engineering, I could try this in Mastering Engineering, although the way the solution's written, Mastering Engineering randomizes these values, so the numbers would be slightly different. I am still going to check the answer. I'm going to put a little pause in this video and go check and make sure that this is on the right track. Well, I ended up checking the solution, and this answer is exactly what they have, so I'm pretty confident in the approach and everything else. I will say I was confident in the approach throughout this, but I was concerned that what they would be doing is a little bit different. Because there's one sentence in this problem statement that I considered rather carefully, but you might have noticed it didn't actually play a role at any point. I never really addressed it, and that is, the man does not move within the culvert. I think that that's not well represented by this solution, simply because we are saying that the moment of inertia about the center of mass is not changing. Or rather the center of mass, is in the same location or whatever. Does not move. Oh. Okay, never mind. If he does not, I thought I was thinking he does move. Yeah, this is exactly the right solution if he does not move. That's a little bit weird. It means he's currently in this position, and it means he's just rolling in it like a hamster that's gripping on the edge of the wheel. So, fine. Yeah, this solution is exactly right in this case. This problem gets a lot more complicated if the man is walking in the wheel and you're assuming that he is staying in the same position relative to the wheel as it moves. So basically, you look at his position at any given moment and it looks like this, even as time passes. That problem is different, and particularly, he's not a part of the rigid body. because he is moving relative to the wheel. If he does not move, as the problem states, within the culvert, then he is a part of the rigid body. That's what we're claiming. And we can treat this as one object and use rigid body motion. If he is moving with respect to the culvert, then we need to treat it as two bodies and think about the forces that he is exerting on the culvert and solve the problem that way. That problem's a little different. It's not so bad. We just have to figure out how he's pushing on things. All right, I'm going to be real careful about what they asked me for. Determine the angular acceleration of the culvert. Looks like I answered that question. That's what we have right here at the bottom. So that's it for this problem. If you have any questions about my solution, feel free to ask. As of right now, I have not made a solution for the last video I intend to post this week, which is one for rotation about a fixed axis. But if you can do this, then you can do rotation about a fixed axis. There's a couple of shortcuts one can take in a lot of problems, so I will be posting a problem to highlight some of those things. All right, everybody, I wish you good luck on this assignment. Get started, and good luck.